Good morning. Welcome back to the course on engineering metrology, and we are in the last week of this course. In this week, I'll discuss about the quality control as specifically statistical quality control. Then we'll have some light on acceptance sampling. So I'll start this lecture with quality control. So what essentially is quality control? Quality control is a procedure or set of procedures which are intended to ensure that a manufactured product adheres to a defined set of quality criteria. So we have a set of quality criteria. Specifically in metrology, we have the measurement limits. Like I said before, I just touched this topic in the previous lectures, that we have upper control limit and lower control limit. And after the production is done or the manufacturing is done and we do the measurements after that, then we see that whether the products which I have produced meet our specifications or not. More than specifications, we will talk about the control limits. There is a difference between specification limits and control limits that I will discuss in this lecture. So, whether it adheres or does it meet, or I'll put does it meet the set of quality criteria or not. Okay. So, quality control is similar to but not identical with another term known as quality assurance. I will differentiate between the quality control and quality assurance in this lecture as well. Okay. So, the quality assurance is defined may be defined as a procedure or a set of procedures which are intended to ensure that a product or service that is under development, that is before the work is complete, before we have actual manufactured, whether it adheres to the standards or not. So, this is quality assurance. This is actually generally before manufacturing. Okay. So, does it meet the specified requirements or not? Quality assurance is sometimes expressed together with quality control or as a single expression. So, sometimes it is said as QA and QC. The quality control department works with quality assurance as well. So, we will discuss this in detail, but before actually coming to the statistical quality control, that is more in the measurements. In 1920s, just after World War I, when it was industrial revolution and the industry was trying to produce more and more goods. So, that was at that point there was a rise in mass production. So, it became important to better define the quality of the products. Originally, the goal of the quality was to ensure that engineering requirements were met in final products. So, later on the manufacturing processes became more complex and quality developed into a discipline for controlling process, and we have the quality control department in every industry, most of the industries it has. So, the department is generally known as inspection and quality control department. Even if you follow the books, if you see the books or if you find the topic, you will find it as inspection and quality control. So, inspection is when we just check the specifications, like we use comparators or we use some measurements and we said okay, yes or no, okay, go or no go, acceptable, not acceptable, that is just inspection. But when we try to plot that, the results which are obtained from inspection here, when we try to plot them and try to see where does the flaw lies, if our process or the manufacturing is not within the control limits. So, if we plot that is statistical quality control. So, it is I think I would like to say it is an extended version of inspection. However, inspection we will not go to that tangent, but we will more focused on quality control. So, in 1920s it started. So, then I can say second milestone was in 1950. In 1950s it was after the Second World War. So, the quality assurance came into play. So, quality assurance was more known as auditing. The quality control techniques which we are employing here, whether they are working properly or not. So, it is kind of an audit. So quality profession expanded to include quality assurance and quality audit functions. So the drivers of independent verifications of quality were primarily industries in which public health and safety were paramount. So this was in 1950s. So in 1980s, the term you people might be knowing, total quality management came into play. Total quality management is maintaining the quality while you are manufacturing. So there are certain techniques, certain tools of total quality management, and people have worked extensively in this. So like quality function deployment, that is the workers or the total productive maintenance, in which the worker who is working is taught to maintain the process as well. The worker who is working in manufacturing, or the operator who is there, he is also skilled enough to maintain or to control the process. Okay, so that is total quality management. So in today's era, if I call it in 21st century, I would call it in maybe after 2000, quality control became an utmost important thing, and we had multiple instruments in this. Instruments means the advanced instruments came into play, like vernier caliper was developed by Vernier, as I said, in the 20th century itself. But now the instruments what we have, I'll also discuss the 3D measurements in the end of this week. 3D measurements, in 3D measurements we can do the measurements for the 3 dimensions, like we can scan, and we'll discuss also, we'll take you to the laboratory here and we'll see the coordinate measuring machine, 3D coordinate, how these are measured. So that came into play, and rapid manufacturing, then rapid prototyping, which is now additive manufacturing. So those things came into play, and people are working on that. So quality control traveled through these milestones. So we'll cover these content in this lecture, the statistical quality control and its classification, then statistical process control, then we'll discuss the control charts. So next we'll discuss the control charts, then I'll discuss what is process capability. Control charts, I'll also like to work on the control charts in Excel, MS Excel. Okay, I like to show you what are the kinds of control charts, there are variables and attributes, different kinds of control charts are there. Then how do we plot those charts in Excel, and if the process is not in control, what step do we follow that after that. So process capability also we'll discuss. Then in the next lecture I'll discuss about the acceptance sampling here. So statistical quality control can be divided into 3 major categories: descriptive statistics, statistical process control, and acceptance sampling. Descriptive statistics, we have discussed this a lot in the previous lectures. Descriptive statistics, these are used to describe the quality characteristics and relationships, and this includes statistics such as mean, standard deviation, range. We have measures of central tendency, then we have measures of dispersion. All those things are discussed here. So SQC, or statistical quality control, is a term used to describe the set of statistical tools. Okay, this I have said before. Now statistical process control involves inspecting a random sample of the output from a process and deciding whether the process is producing the products with the characteristics that fall in the predetermined range. So process control answers the question whether the process is functioning properly or not. Some people say, some authors, if you read books, some people would say that quality assurance deals with statistical process control, and quality control deals with this one, statistical quality control. So SPC do come in the quality assurance part, but some people would describe it in this way as well. I will take it this way, that statistical quality control is there, and when we talk about the quality, the describing the data, descriptive statistics is there, then statistical process control is part of that. So I take it in this context. Then acceptance sampling, what is this? I'll also discuss, that also comes into play here in SQC. So because we use the statistical tools in acceptance sampling as well. Statistical tools mean we can, when we generate the data, we can do some calculations to get some inference, and we can plot the graphs, and while viewing those graphs we can have some information and we can extract some knowledge out of that, and then we can work on that. So that is why statistics term is here. Now next is descriptive statistics. I have discussed in the previous lecture. Okay. So this is, and we have mean, ray, standard deviation, all those things. I'll not go into more details of that. So next is statistical process control methods. Statistical process control methods extend to the use of the descriptive statistics. It extends the use of descriptive statistics to monitor the quality of the product and process. Different types of control charts are used to monitor different aspects of production process. So as we have learned so far that there are common and assignable causes. When we do measurement, as we said, there is a systematic error, there is a random error. Systematic error sometimes we cannot work on, but yes, we are working on the random error. So they are, I would say, common causes and assignable causes. Okay, these are causes of variation in production, every product. So using SPC, we would like to determine the amount of variation that is common or normal. Okay, we use SPC here. It is common or normal. Then we monitor the production process to make it sure that the production stays within the normal range. Within we call it common or normal range. Okay, but the point I am trying to make here is that we would like to make sure that the process is in a state of control, and most commonly used tool for monitoring the process is the control chart that we will discuss. So different type of control charts are there to monitor different aspects of production. So how to develop the control charts? A control chart, also known as process chart or quality control chart, is a graph that shows whether a sample or data falls within the common or normal range of variation. So whether it is a common or normal range of variation, the control chart has upper control limit, it has UCL, that is upper control limit, it has LCL, that is lower control limit, and it has CL, that is center line. So center line might be the true value or something close to true value, so that we need to achieve. So upper control limit and lower control limit are the limits within which our measurements data should fall. So how to construct the control chart, we will discuss this. So we say that the process is out of control when the plot data reveals that one or more samples falls outside the control limits. So I like to just give you a illustration that how the control chart is plotted. This is center line, and we have upper control limit and we have lower control limit. In general, I am not saying for sure, this can be 3 sigma plus 3 sigma, this can be minus 3 sigma. Specifically in case of X bar chart, this value is there. So we have this line here, this is upper control limit, this is lower control limit. Then we will have our process or our points here. Let me say if this is sample size, sample 1, 2, 3, 4, not sample size, this is sample number. This is just a nominal scale 1, 2, 3, 4, 5, 6. Let me say pick 6 points 1, 2, 3. Then it can be something 4 can be here. Then let me say 5 and then 6. I can draw a line here as well. So you can see that there are 6 points, and this value, the specific value, the value number 5 is not in control, is out of control range. So this kind of error, if you can see, sometimes it is random, like the plot is like 1 2 3 4 5 6 7 8, it spike comes 9, then it comes down. This can be random, okay, no non-assignable causes. So this kind of plot which I have just made, I have just picked some random data or I have just plotted something, you can see there is an increasing trend. So it may be inferred from here, I am just saying maybe, it is not for sure, but we have to see the actual experiments and we have to see whether that is true or not, that an error started from here, from point number 3, and it kept on increasing and it went out of control, then it came down. It might be that you know, the value is increasing here, it might be that the instrument that you are measuring with, that might have got some deterioration in that, or the observer who is observing is having some parallax error, any kind of error could be there, but this is a kind of an increasing trend. Okay, this is what the control charts or the graphical or the data visualization do help us to see whether this could be the reason or not. Actual reason we'll find out, we'll actually go to the instrument, we'll find that how the observation is being taken, what error is happening actually there. So we can work on that as well. So next I'd like to talk about the types of control charts. So control charts are one of the most commonly used tools in statistical process control, and they can be used to measure any characteristic of product such as weight, number of pieces in a box, then volume in a bottle, then sizes of the shaft, then the temperature differences, then the temperature in a room in the morning or in the evening. So we can measure any data. We have two kinds of control charts, for variables and for attributes. When I say variables is more close to, or more it will define the continuous data. Any data that we can fit on the normal curve, continuous normal curve, that is a variable. Okay. Attributes that cannot be continuous data, for instance, number of pieces in a box, pieces in box, pieces in second box, so, or the defects in a product, or maybe for instance, if I have manufactured a car, number of defects or the number of defects in the tires of the car, okay, car 1, car 2, number of defects per piece of the car, number of defects per piece, and sometimes proportionally taken, those are variables. Those are, sorry, attributes. Variables can be length, then variable can be weight, all those continuous data that we have discussed. Okay. So the different characteristics can be measured using by control charts, can be divided into two groups, variables and attributes. Okay. The control chart for variables is used to monitor characteristics that can be measured and have a continuum value, like I said, height, weight or volume. A few examples that I could quote here is that, for instance, a soft drink bottling operation is a kind of a variable measure. Since the amount of liquid that is to be filled in the bottle is to be measured, the volume has to be measured, okay, then we know that, okay, this much volume is there, then we close the bottle. So then other examples may be the temperature of maybe the baking oven, if we are doing some kind of experiments, or the temperature, baking oven temperature is a good example. Then the diameter of the pieces that we have manufactured, the size of the gear tooth, and all those, these are variables. Okay. Attributes, so attributes can be used to measure or to monitor the characteristics that have discrete values and can be counted. So I would better put it here. So it is used more for discrete values or can be counted. Okay. For instance, color, taste, okay, I will put it, color for example, okay, then taste, then attributes can be, okay, color, taste, that the answers here can be yes or no, or good or bad, good or bad. Okay. So acceptable or unacceptable can also be one of the terms, but I'll better use that in acceptance sampling. So the attributes, these include color, taste, then smell. The monitoring of attributes usually takes less time than variables, because variables needs to be measured completely. We measure the variable, then we note down the reading, then we can just put it in our descriptive statistics. We can describe, we can put it in a table, then we can plot it the way we like, okay, the way that fits proper to the specific data that we have obtained. So variables are better. This is a kind of a continuous or better continuum data. Okay, these examples here can be height, weight, then volume, sometimes temperature, okay, then pressure, all those things. When I say height, it can be dia or any length. It is better to put length here, any length or linear measurement. So in case of attributes, it can be acceptable, non-acceptable. For instance, number of non-defected pieces or number of defected pieces in a box, then whether the light bulb that we have produced works or not, bulb on, that gets on or doesn't get on, whether the go, no go gauges both are working or not, both are like, is the shaft or the hole or the bearing, for instance, we have manufactured, we need to see the whole size, whether the go, no go gauges are both working properly with that or not. So those can be attributes. So the next is types of control charts. In attribute control charts, we have P chart, C chart, U chart and NP chart. I will take them one by one and try to pick some data and try to plot these in Excel and try to explain you that how do we use this specific kind of data if it is available in that specific form and plot these charts. And for variable control charts, we have X bar chart and R charts or range charts. So I will first take the variable charts, then I will take the attribute charts to give an broad information that in this X bar chart monitor, what we monitor here is the process mean. For instance, if we are doing some casting and we need to maintain the temperature within specific range, and we will measure the temperature at various instances. It has to maintain the temperature for an hour. We can measure the temperature at each 5 minutes, that each 5 minutes in an hour would give us 12 readings, and that 12 readings will take the process mean, the mean temperature. So that is to be monitored. The mean temperature would be taken and the different observations that we have got, we will try to see that whether those are within the limits or not. The two limits, control limits and specification limits, I will tell you. So next is R chart. So R chart is range. Range, like I said, what is range? Range is also the difference between the maximum and the minimum value. So what does this tell? This is actually the measure of the process variability. Okay. So P chart is the P is for fraction defective, the proportion of defective. So I can better put it is used to measure the proportion or fraction defective. For instance, if we are taking certain samples and out of 10 samples, we have seen that 10 samples mean each sample size could be different. We have seen that in first sample, 2 pieces are defective out of 10. In the second sample, maybe 3 pieces are defective out of 20. In the first sample, 2 out of 10 would mean 0.2. This is with the fraction defective. How we will plot this chart? I will just come to that. And C chart is when we have the number of defects. Like I said, number of defects in the car or number of defects in the specific section of the car when it is manufactured. So it is number of defects. So U chart is when we have number of defects, it is C chart when we have defects per unit. When we are trying to monitor defects per unit, it is U chart. So the difference between U and C chart, we will try to see these are very similar because we are dealing with defects in both the charts, but the difference is that when the sample size is different, we use U chart. When the sample size is same, we use the C chart. For instance, the sample size, if I pick 10 samples and each sample has 20 pieces in it, okay. So out of 20 pieces we are now trying to note the defects, number of defects. So it will use C charts, but if we are picking random number of sample sizes, then U chart can be used because we will take the defects per unit. Let me say first 20, then 30, then 10, maybe we will try to normalize data and we will bring it to the single scale. Next is NP chart. So NP chart is number of defectives in a sample of inspection units. I would put number of defectives in sample of inspection units. So these are the things which we are trying to monitor or control in these specific charts. So let's meet in the next part. Thank you.